All right, this is Unit 3, Lesson 3, Rational Exponents. And by the end of this unit, you should be able to identify what a rational exponent is, and then write radical expressions as expressions containing rational exponents and vice versa. Okay, being able to switch between radicals and rationals. All right, so we're going to be looking at something like this, where you have a base raised to a fraction. So that's pretty much what a rational exponent is. It's a fractional exponent. All right, and we have this little caveat right here. It tells us that b cannot be less than 0 while n is even. So if we think about what that means, it's already saying something we already know. That's saying that you can't have a negative radicand with an even index and get a real number. So that's just kind of pointing that out to us again. All right, so let's take a look at our examples and figure out what a fractional exponent is. Okay, so if we look at 36 to the 1/2, the number on the top is your exponent, the number on the bottom is your index. What that means is this is saying the same thing as this. Okay, so the 2 is my index, and we know for a square root we don't have to write the 2. And then this is my power. So that's just saying, hey, take the square root of 36, which is, of course, just 6. Our next example has 64 to the first power as our top, so that doesn't do anything. But then it's saying, hey, take the cube root. So we're taking the cube root of 64, which in turn is just 4. Okay, so the fractional exponent is another way to write a radical. These are the same thing. Okay, if I see a cube root of something, I can write it to the 1/3 power. And that's going to help us more as we get into simplifying things where we have to rationalize our denominators that have bigger indexes. It's an easier approach. Also, when we're combining things, sometimes it's easier to write it as a fraction than a radical to help us. All right, our next example has a negative. And if you think back to your exponent rules, we cannot write things with a negative exponent. So we first want to take care of that. All right, so let's backtrack for a second and think about this. All right, so if I had x to the negative second power, how am I going to write that to get rid of that negative? That's right, I'm going to write it with this in the denominator. So this ends up being 1 over x squared. So if I move something to the other side of a fraction, it becomes a positive exponent. Now I can do the same thing if my exponent itself is a fraction. So if I have x to the negative 1/2, I'm just going to rewrite that as 1 over x to the 1/2. Okay, and then we'd have to simplify, but we'll get to that later. So doing the same thing here, it's just my base is a number as opposed to a letter or a variable. So this is the same thing as 1 over 49 to the 1/2. Meaning, hey, take this 1 over the square root of 49, which is just 1/7. All right, so I took care of that outside exponent first, moved it, and then simplified. All right, if I notice here, I'm doing the same thing, guys, but inside my parentheses, I have a fraction this time. So if I'm taking care of this negative, it's saying flip it around. That's what I did here. I flipped it around. The 1's moving to the bottom, the 8's moving to the top. So this is the same thing as 8 to the 1/3. Okay, 1/8 to the negative 1/3 is 8 to the 1/3, or the cube root of 8, which is 2. Okay, let's take a look at an application problem. So we're going to use this formula, and this n is supposed to be a power in exponent, so just please raise that up. It says a gallon of milk costs $2.69. How much will the cost of the gallon of milk increase by in 6 months, assuming a rate of inflation of 5.3%? All right, so we're just going to plug things into our formula. This big C represents what it will cost. The little c is our current cost, which is $2.69. The R is our rate of inflation as a decimal. So remember, when you're going from a percent to a decimal, you can do your Beyonce to the left, So it'll be 0.053. And we're going to raise it to an exponent. Please be careful here. N represents the number of years. I'm told was given information in months. So 6 months, how am I going to represent that in years? There's 12 months total in a year, so that's going to be 1/2. So here's our fractional exponent. All right, now we could just plug and chug that into our calculator. And when you type that in, you end up getting 276. Okay, so we can use fractional exponents to help us. All right, so let's keep going. And how are we going to use this? When are we going to simplify all this good stuff? So remember before I said when you have a fractional exponent, the number on the top is your exponent, what you're raising it to. The number on the bottom is the index. Okay, so I can represent something three different ways. So let's take a look at x to the 2/5. So this is with a rational exponent in that form right there. I can also write it as a radical in two different ways, okay? I can write it this first way right here where I'm saying, okay, I'm going to take the 5th root of x squared. So the denominator is your index, the numerator is your exponent. That is the same thing as if I did this. Okay, they're all the same thing. If I were to simplify them, I should get the same answer every time. The difference between your two radicals is how you're doing the simplification. And we'll take a look at that with our numbers in one moment. But I find this method easiest. What this implies is I'm taking the root of a number first and then I'm raising it to the exponent versus raising it to the exponent first and then taking the root. Neither is wrong or right. I just find this method easier because what I'm doing is I'm breaking this down to a smaller number first and then raising it to a power, as opposed to raising it to a power, so bigger number first and then taking a root. I just find this way more manageable to work with, but it's up to you. Okay, so let's take a look at some numbers now. So we have 27 to the 4/3. Okay, so if I want to simplify it, I'm going to go ahead and put it in my radical form. So let's take a look at the longer or the bigger number way first. So let's go ahead and raise it to the 4th power first. And if I do 27 to the 4th power, I end up having to find the cube root of 531,441. And then when I take the cube root, I get 81. Okay, if I do it this way, I take the cube first and I get 3 to the 4th power, which is 81. So it's the same thing. It's just the second method I worked with smaller numbers, which were perfect cubes and powers that I knew off the top of my head versus, getting stuck with some big number. All right, so go ahead, pause the video. Go ahead and try numbers 1 and 3 on your own. Just a heads up, that's problem 1. That's not a decimal. 2 is the example we just looked at, so you don't have to rewrite that again. But go ahead and try to evaluate those on your own. First, write it as a radical, and then evaluate it. I'm going to pause the video as well. All right, you can take a look at my work. In both of them, I took the root first to make my numbers more manageable and then raise them to the outside exponent. So I did the square root of 36 cubed, which got me 216. And then I did the 4th root of 81 cubed, which gave me 27. All right, so we're going to use this understanding to help us simplify some expressions now. Okay, so let's take a look at some examples. All right, so some rules with simplifying expressions. When all is said and done, how do you know you're done simplifying? Well, you no longer have any negative exponents, okay? Those are a no-no. You don't have any fractional exponents in the denominator, okay? Because remember, that means you have a radical in the denominator, and we know that's not allowed. You don't have any complex fractions, so a fraction within a fraction. And the index of any remaining radical is the least possible number. For example, you don't have something like the 20th root of x to the 10th. While I can't break that down, I notice that both my index and my exponent have a common factor. So really, if I divide both by 2, it's this, okay? But we'll talk more about that later and how we got there and how you know what to do with it. All right, so pretty much we want to be writing our answers in simplest radical form when we're simplifying it. So each problem has a new task that we have to look at and figure out, well, what do we need to do? All right, so if looking at this first one right here, I need to write this in simplest radical form. Well, if I notice, none of my bases are the same. I have a 4, an A, and a B. So simplest radical form, I want to combine them and write them as one radical. Right now, the way that's written is I have the cube root of 4 times the square root of A times the 6th root of B to the 5th. Okay, so I can't combine them under one radical because I have different indexes. So our clue here is, okay, let's write these with a common index. So what am I going to do? That's why looking at it in a fraction is easier than looking at it in this way for right now. Okay, because I can make common fractions. I can make equivalent fractions with a common denominator. So I notice all of these can get a denominator of 6 because 3, 2, and 6 all have a common factor of 6. And don't forget, if you change a denominator, you need to change your numerator. So to go from 3 to 6, I had to multiply by 2. So 1 times 2 is 2. To go from 2 to 6, I multiplied by 3. So 1 times 3 is 3. To go from 6 to 6, I multiplied by 1. So that stayed the same. Okay, so now I have a common index, so I can write them all under one radical with an index of 6. So I have 4 squared, a to the third, b to the fifth. My last step would be to simplify anything I can. All right, well, 4 squared, I know I can do some math there. So that's going to give me 16. Now from here you have to say, okay, if I broke anything down, can I make groups of 6 of a kind? Can I reduce this radical? No, you can't. 3 A's do not make a group of 6, 5 B's don't. So I'm done. I don't have any fractions. I don't have anything in the denominator that shouldn't be. I have no negative exponents. Therefore, I'm done. Everything's written together as one radical. I am done. All right, now, this next example is very similar, except they all do have a common base. So when I put them under my radical, I can go ahead and combine them. So why don't you go ahead, pause the video and give it a try. Find common denominators for your exponents first. All right, and take a look. So I could rewrite them all with a common denominator of 20 and adjusting my numerators accordingly. And then because they have the same base, I can actually add my exponents. We couldn't do that in the last problem because the bases weren't the same. 4a and b aren't the same. These are all x's. So when I combined them, I got 29 over 20. So I went ahead and put that into a radical, and then I reduced my radical. If I have 29 x's, I can take out one whole x with 9 left over. All right, looking at my next example. So let's take a look. Let's see what can be done. I only have one base, so that's nice, but I notice a negative. Can't have a negative. So with that being said, this negative is telling me that this is the same thing as this. All right, so am I done? No, because now I have a fraction in my denominator. And even if I were to rewrite that in simplest radical form, I would have a radical in my denominator. So what do we need to do here? We need to rationalize that denominator. Now guys, you can go ahead and write that in simplest radical form and rationalize it the way that we learned, but I'm going to show you another method on how we can do the same thing but in an easier way, okay? I'm just going to go ahead and, erase this so that I have some room. Okay, pause on that for 1 second. Let me show you something. When we looked at our example the other day, well, let's take a, so we have 1 over, let's say, the cube root of x. So to rationalize that denominator, we talked about, well, hey, if you only were to multiply that one more time, it wouldn't get rid of the radical, because then I only have the cube root of x squared, which isn't enough to get rid of it. I can't take the cube root of x squared. We needed to multiply another time, sorry, by the same thing up top, but we needed to multiply another time in order to get rid of that radical sign, right? Well, let's rewrite these using our rational exponents and see what happens. So this will be the same thing as if I wrote, now I'm going to write next to it, x to the 1/3, right? Because it's 1 and 3. X to the 1/3, x to the 1/3. So when I combine all those together, and notice they're the same base and I have the same index, so I can just easily add them. 1/3 plus 1/3 plus 1/3 is 1, x to the first. That's the same thing as when we multiplied all of them out in radical form. I'm getting the same thing. I'm getting rid of that radical. I'm getting rid of a rational exponent. So as opposed to, back to our W problem, as opposed to simply writing those out in radical form and multiplying, 4 more times, which we can totally do, but it's going to get long, we can simply multiply to create an exponent of 1 whole. So what do I need to include here W to the what power? To the 1/5. Why? Because W to the 4/5 times W to the 1/5 is W to the 5/5. Because remember, when you're multiplying common bases, you're just adding your exponents. So in that case, I end up getting W to the 1/5 over just plain old W, which if I wrote it out with my radicals, I would get there eventually too, just eventually. So am I done? No, because I have a fraction. So let's go ahead and rewrite this. This is the 5th root of W over W. Now I'm done. There's nothing I can reduce under that radical. Can't cancel anything. I am done. Got rid of my negatives, got rid of the fraction or the radical in my denominator. All right, please pause the video and try the next example. It's looking at the same concept. One thing, just please be careful here. Notice just the y is raised to the exponent, not the x. All right, I'm going to pause the video as well. All right, so take a look. So first thing I did was I moved my y to 1/8 to my denominator. Okay, that got rid of the negative. Then I went through and multiplied by y to the 7/8. Why? Because that's going to create one whole, my exponent in my denominator, which gets rid of the fraction. I created fraction up top, which is fine as long as I just translate it to radical form, which I did right here. Okay, the x doesn't get affected because it's not raised to the exponent. All right, let's take a look at our next example. So looking at it, I have radicals. I have a division. I don't have any negatives, and I don't have any common bases. So right now, the only thing we could do is not much. Well, let's think about this. We need to simplify because I've got a radical in my denominator. So we can go through and rationalize that out. That's fine. That's 4 to the 1/8. So we can multiply by 4 to the 7/8. But that's going to get ugly. Not wrong, but ugly. So let's think if there's another way we can do this. We talked about trying to divide first before. Can I find a common base here? Okay, so first let's write this as a radical. I've got 32 to the 1/10 over 4 to the 1/8. Common base. I notice that both 32 and 4 are powers of 2. For example, 32 is the same thing as 2 to the 5th. 4 is the same thing as 2 squared. I'm just rewriting it using an exponent because now I have a common base of 2. So if I were to rewrite this with rational exponents, that's 2 to the 5/10 or 1/2. Down here, I have 2 to the 2/8 or 1/4. I'm just reducing my exponents to make it a little bit easier. All right, so I've got 2 to the 1/2 over 2 to the 1/4. Now I have a common base, so I can use my division rules. Anytime I'm dividing common bases, I can subtract my exponents. 1/2 minus 1/4 leaves me with 1/4. If you weren't sure of that, then just write them as common fractions and subtract. You would get 2/4 minus 1/4. Same thing. Almost done. Just got to write that as a radical. 4th root of 2. All right, we're going to take a look at 2 more examples together. Okay, so look over here, please. First thing to notice, negative. Get rid of that negative. So I'm going to move this downstairs, which gives me 1 over 5 to the 1/2 times the 2 that radical 5 that was already down there. Okay, so I'm not done because I have a fraction and a radical in my denominator. Well, let's think about this. What can I do? So when you get here and you're like, I'm not sure what to do, try something. Meaning if I have a fraction, try changing it to a radical. If I have a radical, try changing it to a fraction. See what happens. So 5 to the 1/2 is the same thing as the square root of 5. Or you could have done 2 times 5 to the 1/2. You could have, changed the radical to a fraction exponent, either way. But I notice that's going to help me because now if I just multiply these, they have the same index, so because they're both square roots. So when I multiply, I get 1 times 2 times the square root of 25, which is really 2 times 5, which is 1 over 10. No more fractions, no more radicals, no more negatives. I'm done. Okay, so take care of negatives first. Look for common bases if it's division. If it's multiplication and you have something in your denominator, get rid of it in your denominator by trying to rationalize it, or in this case, we can multiply it. It was already rationalizing itself. All right, my next problem. I've got 1 over m to the 1/2 minus 1. Okay, so I've got a fraction in my denominator. Now, I can't simply just multiply by m to the 1/2 and get rid of it because of the binomial. So hint, use a conjugate. If you want to change this to a radical and multiply it that way, you can. If you want to keep it with a fractional exponent and multiply, you can. It doesn't matter. But we're going to use our conjugate. So guys, this is the same thing as this, right? So whatever form you're more comfortable in. So to go through and multiply, we're going to use our conjugate, which we learned last time. Oops, I forgot to change the numerator. So that's going to be the square root of m plus 1 as well, and multiply through. So when I simplify that numerator, I get the square root of m plus 1. And in my denominator, the square root of m times the square root of m is the square root of m squared, or just m. Positive 1 square root m minus 1 square root m, so they cancel out. They're supposed to. That's conjugates. Negative 1 times 1 is negative 1. I don't have anything in my denominator that I shouldn't. I don't have any negative exponents. I am done. And no, you cannot cancel these out, okay? This negative 1 is attached to the m. Positive 1 is attached here. I'm done. That's it. All right. And I would like you to do this problem right here. Pause the video and give it a shot on your own, and then see how you did. This is a tricky one, but you can do it one step at a time. Hint, work with the inside first. Get rid of your negatives inside first. But there is, of course, more than one way to do it. There's so many different methods you could go here. All the same method, but different routes. So go ahead and pause the video and give it a try. All right, here we go. Ultimate answer is x over 4, so you can check yourself. Okay, if your work is a little bit different, that's totally fine. So what I did first was I adjusted my x's. Now please be careful, this 2 is not raised to a negative yet on the inside, so I haven't flipped it yet. I just flipped the x's because those are both negatives. Then I went ahead and subtracted my exponents. 3/2 minus 2, or 3/2 minus 4/2, gives me an x to the negative 1/2, but then because that's a negative, that one down below. Then I took care of the negative on the outside, and you could have kind of done some of these at the same time. But the negative on the outside, I said, hey, flip them again. So they flipped. And then I raised things to the outside exponent. So remember, an exponent to an outside exponent, you multiply and you get x. And then 2 squared gave me 4. All right, that is all.